Hi, Chem 100. This is the beginning of Module 7, our acid and base chemistry, and our last module for this course. So let's go back and do a little reviewing. Sodium hydroxide is a solid at room temperature, and water is a liquid at room temperature. So what types of bonds exist and then draw their structures? So we know that sodium is a metal, and OH hydroxide is a polyatomic ion, but we know that because Na is a metal, that this is an ionic bond. Also, because of its ionic bond, that it is a polar bond. And then when we look at water, and we know that oxygen has those two lone pairs, and that because of the electronegativity difference, that because the oxygen is slightly negative, that we have this dipole pull to our slightly negative oxygen. And because of that electronegativity difference, we know that this is also polar, and that it is a covalent compound, right? They're both nonmetals, and we know the electronegativity difference makes it covalent. So why would we expect them to mix? Well, because both of these compounds are polar, we know that likes mix. So both are polar. And what type of interaction are they going to have with one another? Well, what's going to happen is that my Na plus is going to be surrounded by my waters, because my slightly negative oxygen is going to be attracted to that positive sodium. And then my slightly positive hydrogen is going to be attracted to the OH minus from the hydroxide. So my hydrogen from my water is going to be attracted to my OH minus. So that's our interaction. And so the balanced chemical reaction with our states of matter, when we write this out, we're going to have NaOH, which we said was a solid, plus H2O as a liquid. And then what's happening here, oh, and I forgot my Cl. There's no Cl, sorry, it's sodium hydroxide. My NaOH is going to disassociate, so I'm going to be left with my sodium ions that's surrounded by water, and so we would say Na plus aqueous, plus my OH, again surrounded by water, so it is aqueous. And my water is still the same, so I can still write H2O liquid. We could also choose, since nothing happened to the water, that water surrounded the sodium and the hydroxide ions, we could choose to leave out the water and just write the dissociation of sodium hydroxide down into sodium ions and hydroxide ions. Either one is fine. All right, let's look at another example. So we have HCl as a gas at room temperature and water as a liquid. So let's look at what types of bonds these two exist as. So I have HCl, so I'm going to have that bond there, and chlorine we know has 3 lone pairs. And if I look at the electronegativity difference between H and Cl, it should be 0.5. And so we know that that is a covalent And we know 0.5 also makes it polar. Very slightly polar, but it's still polar. So there is a, chlorine is therefore slightly negative to my slightly positive hydrogen. And then we just talked about H2O. We know that the electronegativity difference there makes it covalent and polar. And on top of that, we can even be more specific and we can say that this is hydrogen bonding. The same would be true for the last slide. Looking back at this H2O, this would also be hydrogen bonding, which is just pretty much saying that it's a very strong covalent bond, right? Hydrogen bonding is one of the strongest intermolecular forces. So if we look at this, we've got our, oh, I meant to put the 2 lone pairs for oxygen and show my dipoles here. All right, so why would we expect these two to mix? Well, similar to the last one, they're going to mix because they're both polar, right? Likes mix. And then let's show how they're going to mix. So we know that I have, again, my H and Cl, and there's my dipole like this, so this is my slightly negative. And if I look back at my H2O, my slightly positive end is my H, correct? So we're going to have my HOH because of this line. We're going to see this line up where my slightly negative chlorine is going to be attracted to that slightly positive H. And then this oxygen, which is slightly negative, is going to be attracted to the H on my HCl. And so we can see this lineup. Where's another water here? There we go. And so what we're going to see happen here, we can see all of our dipoles lining up and kind of going all in the same direction, right? Because my slightly negative oxygen is going to be attracted to the slightly positive H. And what's going to happen here is that negative O is going to grab that positive H. And this negative O from that water is going to grab that H. So when we write this balanced equation, I'm going to have HCl as a gas plus H2O as a liquid. And what's going to happen here is this water is going to grab that extra hydrogen. So we're actually going to have H3O plus, and that's aqueous, plus, and then my poor little chlorine is going to be by itself aqueous, surrounded by those waters. So this H3O plus is called hydronium. And this HCl is an acid. And looking back here at our previous slide, this NaOH is a base. So we are going to talk more about that on this next slide. All right, so what is a base? First, when the most common form is when the base is placed in water and it forms the conjugate acid and the OH, similar to that first slide. If we went back and looked at this example, we saw that my NaOH we can see here the waters surround my Na. My NaOH disassociated, and I could continue drawing and see that my slightly negative O is going to be attracted to my positive H and have my other two H's over here. Same with my OH, and I forgot to show that very well, but my OH negative, so that means that the hydrogen part of my water is going to be attracted to the OH. Same here, if I were to draw another, well, here we go. My H2O is going to be attracted to the H part of the water and the H part of this water. So looking here, this would be an example here where my Na is going to be disassociated and my OH minus. And again, I can choose to leave off writing H2O. It's there. The water is surrounding both of these ions when they've been disassociated. Another type of base, a little less common, is what's called a Bronson-Lowry base. So OH is still formed, but it's because we've accepted a hydrogen ion. And what that means is here I have NH3, which is ammonia. And I am including water. So ammonia is a base, but it's not as easy to pick out as the hydroxide was above it. We still end up with the hydroxide because what happens here is ammonia grabs one of these hydrogens from water. So it is accepting an H plus, and it's not bringing it's not bringing the O, which is oxygen negative, it's just accepting the H plus. So over here, instead of having NH3, we have NH4, and because it brought that hydrogen, it's going to be positively charged. And then that leaves us with, right here, we have OH minus, which is our hydroxide, so if I were to write this reaction out, again, I have my NH4, and I'm just going to put aqueous because it is surrounded by water, and my OH minus, my hydroxide, again, aqueous because it's surrounded by water, and I'm just going to leave out that water. Again, I'm not going to write H2O on the right side and have it on the left side. So what we call these, we know obviously this NaOH, because it's got the OH right there, we know that this is a base, and my ammonia we know is a base, and both of these we can see they result in this hydroxide. And right here we said when a base is placed in water, it forms a hydroxide and a conjugate acid. So both of the other product that we have here that's not the hydroxide are called our conjugate acid. So that would be my Na plus and my NH4 plus. All right, so when we look at acids, what's an acid? When an acid is placed in water, it forms a conjugate base and H3O plus, hydronium ion. One real common feature to be able to recognize acids is if we have this compound starting with an H. That is a pretty distinct feature. You can rely on that being an acid. So we have my acid here, and HCl, similar to the second slide, my HCl is going to break apart here and disassociate. So I'm going to have my Cl minus surround my chlorine surrounded by water plus my H2O is going to grab that other H, so I'm going to have H3O plus and aqueous. And so here we go. There's an example of, I'm going to have my H3O plus, and then if this is my acid, it's going to form that conjugate base. So this is my conjugate base. And for my second example, we can see here this HNO3. So here's my hydrogen. So this other way to tell if it's an acid is if it donates a hydrogen ion to any other substance. So this hydrogen that's on my HNO3 is going to donate that hydrogen to water. So we can see over here, so that my products are just NO3 minus, and that H went over to my water to give me that H3O plus. Again, both aqueous. And so there we go. Both products contain my hydronium ion, my H3O plus, and both also contain a conjugate base.